Você tem já. So, good morning, everybody. It is a pleasure to me to start this control theory session. So, the first speaker will be GERALDO Silva, and he will speak about the title of his talk is On the Sufficiency of the Maximum Principle for State-Constrained Optimal Control Problems.
Okay, thank you. So first I'd like to thank Alfredo for the invitation to be here to give this lecture, to give this talk. I'm going to talk about the sufficiency of the maximum principle of Pontryagin. This topic is something I started to work a few years ago after, well, my interest in this was basically because of Valeriano, but then I became more interested when I heard that Pontryagin, when he started to work with this maximum principle, started to generalize the necessary conditions from the linear quadratic problems to the nonlinear general case, because he was not a control theorist. At that time, control theory didn't exist. But he thought that the maximum principle would be also a sufficient condition. But of course it wasn't. I'm going to show here a simple example where the maximum principle is not a sufficient condition. But then, after that, people started to think, which is the weakest condition where the problems on the data should satisfy so that the maximum principle is a sufficient condition. So to answer this question was the aim of this research program. Okay, let's say, so the object is an optimal control problem. Here we are minimizing function g, which depends on the initial state and the final state. We have a dynamical system here, which is dependent on the control. So given a control, we have a response, which is the trajectory, x, and the state final, the terminal states, initial and final states are constrained to a set C. C lives in Rn times Rn, and we have also here these state constraints, and the control are also constrained to some set which depends on the time as well. So here are where the functions are defined. U as depends on t is a multifunction as well, and this time interval t0, t1 is fixed. It can be moving as well, but it is fixed. So the person who started control theory as we know now was this person here, Lev Pontryagin. Okay, just to put here. The result he and his team, of course, Mishenko, Gram-Klelides, and then later Mishenko, Boltiansky, provide this result here, which was something new at that time in the early 50s, and not early, but late 50s, which says the following. Given an optimal process, a process is a pair of control and state. So given this optimal process, there exists an adjoint variable psi, psi, and lambda, which is 0 or 1, obeying this adjoint equation. Here, this is we call Hamiltonian or Pontryagin function. The Hamiltonian is given by this formula here. And so it satisfies this adjoint equation. Here's the boundary and transversality conditions. And this condition here is the maximization of the Hamiltonian with respect to the control. So it is maximized when you fix t, u over u of t, there should be t here. So you maximize so over u in u belonging to u of t here. So this is the maximum principle, what they call maximum principle, the set of necessary conditions for the optimal control problem, without state constraints. Here we are supposing there are no state constraints, okay? There. So we call extreme control process a process that satisfies the maximum principle. And as I told in my initial words, this extreme process may not be optimal. And I repeat again, Pontryagin thought it would be also a sufficient condition of optimality, but however, it is not. And this is a simple example that shows that when you have nonlinear dynamics, the maximum principle is not a sufficient condition. So this example is simple. We have minimization of the second state here in the final second state. This is the simple dynamics, where here's where the terminal and final state. And u can be in -1, 1 here. So you see that the trivial process obeys the maximum principle. It's easy to check, but it is not optimal. So now I come to the question, what are the weakest requirements that the control problem data should obey so that the maximum principle becomes a set of sufficient conditions of optimality? So this is what should be answered. And one of the first person to give a partial answer to that question was Arnstein, SV Arnstein, 2011, where he proved that for a certain compatible feedback control, the maximum principle became a sufficient condition, okay? But a full answer was given here by Oliveira and Silva in 2012, published in 2013, for fixed time control problems without state constraints. And here we extend this result for problems with state constraints, okay? This is the purpose of the lecture here. I need to drink some water, just. Well, so for providing these conditions, weakest conditions for to try to find the conditions, we came back to see what people did for mathematical programming problems. So this is why generalized convexity comes into place. In finite dimensions, when you have a convex function, we know if it is differentiable, it satisfies this inequality here. And Hansen saw that if this x minus y here, this x minus y here plays no role. You can change it for, okay, that will go from the beginning. If y is a stationary point, okay, the gradient is 0. You can see that f of x is greater or equal to f of y for all x in D. That means y is a global minimizer. But when we look at this, we know, you see that x minus y here plays no role. So it can be replaced by a non-zero function, eta of x and y. Any function can be put in this place here. And you get this inequality. Functions obeying this type of inequality here would have the same property that a stationary point would be a global minimizer. Okay? So this class of functions were called invex functions, not by the person who published the first work on this subject, but by someone else called Craven. Craven, I don't know how to pronounce Craven, in the same year. So he coined this word invex for, here is the reason why he called these invex functions, is because if you have a convex function, you compose it with the differentiable function, which is onto, well, the derivative, the Jacobian is onto, we can somehow distort, I think this is the word in English, I don't know, distort the graph of the function, and this function is no longer convex by this composition here, but it still satisfies some this inequality here, which these functions f then becomes invex. You distort the graph of the function, and it becomes an invex function. It obeys the same inequality here and has this property that every stationary point is a global minimizer for the function, okay? Later then, in 85, Craven Glover provided this result which says that f is invex if and only if every stationary point is a global minimizer, so for only a function. Now we go to the mathematical programming problem with the constraints here, g of x less or equal to 0. And if these functions are convex, both of them obey this type of inequality here. Here is the Jacobian of g, because g is vector valued here. Then we can do something similar, right? F of x minus f of y plus mu times g of x minus g of y here. And this mu is the Lagrange multiplier. If we assume here some kind of constraint qualification for this convex problem, you have KKT conditions, so we can choose lambda equal to 1, and the rest of the multipliers, because we have only inequalities, would be non-negative here. Then we use the fact that these functions f and g is convex, we get this inequality. We can then arrange terms here and have this. And if y is a stationary point, this is 0. You can easily get that f of x is greater or equal to f of y for all x in D as well, okay? We have the same property then if this mathematical programming problem is invex because all the functions are invex, then we have that all stationary points are optimal, okay? Sorry, I did some confusion here. We are saying that we can replace this x minus y here by any x here, and we have the same kind of inequality. We have this. We can have this inequality here and have the same property that all stationary point is a global minimizer. And problems which satisfy this we call invex. We are copying the convex programming problems. Okay, so if they are invex, we call invex problem. So, but the thing is, invex problems is a small class that obeys this property that every stationary point is a global minimizer. There are no invex problems which has the same property. So this class is larger than invex problems. And this was then later, in 85, Martin introduced this notion of KT invexity for mathematical programming problems. And he just left the objective function as as invex, and only this inequality here should be satisfied by the constraints. And then we have this, the Jacobian times this eta is less or equal to 0. Eta here should be the same function. For all functions, we should have just one eta. So this type of problems was called KT invex problems, and here he proved that every stationary point then is a global minimizer if and only if the problem is KT invex. So this is the largest class for mathematical programming problems that this property is valid, okay? So this is for mathematical programming problems. Then we try to generalize this for optimal control problems. Not directly, so things are a little bit different. Okay, this program we started some years ago. First, we worked as usual with simple problems, smooth problems, and we could get some kind of KT conditions for the optimal control problems. Then Valerian did for multi-objective problems, and recently, of the conditions here we didn't call invex. We used this name MP sud invex, which is we are going to show later is not like invexity. It's something different. Okay, we call sud invex. MP comes from maximum principle, so the process should satisfy the maximum principle, and the problem should satisfy some conditions which we call, so then MP sud invexity. Okay, so we, as I told before, we then generalize this result for optimal control problems with non-smoothness, but without state constraints. And here, our objective then is to look at this problem with the state constraints here. So the same problem, state constraints here. This is what we are going to look now. Let me stay on the other side this time. So now we talk about the hypothesis. We assume that function f here is not objective function anymore. I mixed up here some notation, but f here is the vector field. So the vector field should with respect to the time and the control, should be measurable with respect to the Lebesgue-Borel sigma algebra. This for each x in Rn, and there must be a function k defined on the graph of U, such that this vector field with respect to the state should be Lipschitz, and the graph should be measurable with respect to these algebras, Lebesgue and Borel, and G here is the objective function, and G should be Lipschitz, and H, which is the constraints, G should be upper semi-continuous, and Lipschitz with respect to the state, and this Lipschitz continuity is with the constant K, which is independent from T. And here we have the Hamiltonian now. I'm not using psi, I'm using P now. Okay. And the maximum principle Pontryagin now for this problem with the non-smooth data and state constraint will be would be read like this. So we have an optimal process. Given an optimal process, there exists lambda, which is 0 to 1, and there is an absolutely continuous function p, which is the state, which is the co-state variable, a Borel measurable function gamma, and a non-negative measure obey all of these. The first inclusion here is the is the adjoint equation. This is the maximization of the Hamiltonian, and here we have this inclusion of this function in this. We call this positive subdifferential of h with respect to the state. I'm going to define this in the next slide. And we also have that the support of the measure should be included in this set. In this set here is the set of all states where the constraint is active. And here is the usual boundary and transversality conditions put together. This non-triviality of the multipliers. And here's what means Q given like that, because we have here the constraint, state constraint, so this would appear. This function Q is left continuous. The way it is defined here, it is no longer absolutely continuous, but we have P, which is absolutely continuous, plus something here, which gives non-continuity of the Lagrange multiplier. This is the set of times where the constraint is active, and here's the definition of this positive subdifferential of the constraint. So we see positive because it is defined as a convex Hall of all limits where the gradient exists with respect to the second variable here and converge to this xi, but this convergence here is only by points where the constraint is positive, is violated. So this has, this maximum principle can be found in many classical books. There are many books, I just put here 3, but there are many others, Now we start with the definition, which is the main objective here of the talk. We start now, So these functions or these objects here are the multipliers. When they exist, satisfying the last conditions, we say that the process is an extremal process for the optimal control problem. And when this first multiplier here can be chosen to be 1, we say that the process is a normal extremal process. And then the problem is said to be normal at the process, at the specific process. And we say that the problem is normal when it is normal at any extremal process. All process we can find a set of multipliers, or these multipliers with lambda equal to 1. And in control problems, if you don't have terminal constraints, given like that, the optimal control problem is always normal. You can always choose lambda equal to 1. Now we come to something we need for the definition of pseudo-convexity for the problem. First, we consider this variation of f with respect to the control. Here, so this is we call this a variation, So this is for all lambda, alpha between 0 and 1, alpha between 0 and 1, then we have this difference here. So take these multipliers in this set. This is only to say where they live. Lambda 0, 1, lambda 0, 1, p lives in this space. Gamma is a bottom measurable function, and mu is a non-negative measure. So we take these multipliers in this set such that all of this is satisfied, and this is almost the necessary conditions which were written previously, but the maximization is not here. Everything else apart from the maximization. So this is this set lambda here is saying this, okay? These functions which satisfies almost all the conditions of the necessary conditions apart from the maximization. So now we come to the definition. Say that the problem is MP sub invex. If given two admissible processes and alpha is 0, 1, and this point or this vector functions here in this set, there exist maps eta and xi obeying the following. If this inequality here is valid, then we should have this other inequality here, which is given by these two integrals here. And also, we have that this point, eta of T0, eta of T1, should be the tangent cone. The tangent cone here we use, for simplicity, the Clark's tangent cone. We should have this inequality, and this variation here, or this perturbation of the optimal control should be admissible, okay? Okay. When the conditions, previous condition is true with lambda equal to 1, the problem is said to be normal, MP sub invex, when you can choose lambda equal to 1. So then we come to the sufficiency, which says, if the OCP is MP sub invex, then every extremal process is an optimal process. So this is the result. I'm not going to show the proof, but we have this on the paper. And then we also prove that if the OCP is such that every extremal process is an optimal process, then it is MP sub invex problem. Here I wrote normal because if the problem is normal, or if the extremal is normal, then the problem is normal, MP sub invex. I wrote two results in one, okay? So with the two theorems, we have then, we have then this theorem 3, which is just theorem 1 and 2 together. So we have the if and only if thing here. So OCP is MP sub invex if and only if every extremal process is an optimal process. So this generalized, okay, this generalizes the, gives you the complete picture of when the maximum principle is a sufficient condition. So this should be the conditions that the problem should obey. And this result is if and only if. So it says there is no larger class that can obey this condition. But we also found a different way of defining MP sub invex, which my time is over. I'm not going to talk about that. Just leave it. So, but we proved that this condition is somehow equivalent to the previous one. Not equivalent, but if the problem is normal, they are equivalent. Okay, I finish here.